Okay, so today we are going to be first just going through an example of a transformer encoder network called BERT, and we'll talk about the pre-training stage and also like how you might want to fine-tune a model like BERT, but just very briefly. And then after that, we will cover tokenization, which is the process by which we split an input string into discrete units that are then passed into the transformer. So we got a lot of stuff to cover today, so let's just get started. First, I wanted to briefly summarize what we discussed in the last class towards the end when we were contrasting pre-training from post-training. And I wanted to just draw a diagram to explain how we arrive at models like ChatGPT today. So when we're talking about pre-training, we generally start off with a randomly initialized transformer decoder. So remember here that a transformer has all of these different parameters, right? It has the query key value projections for each head and each layer. It has the big feed forward matrix W sub z for each layer. It has the word embeddings and the output softmax layer. And so all of these parameters are randomly initialized to begin the pre-training process. Then what we do is train on a giant data set to obtain a new model that we'll just call the pre-trained transformer decoder. So now all of the parameters in this new transformer that we've got as the output of this process have been optimized for next word prediction on this gigantic training data set, right? We were talking about things like the internet and books, textbooks, and so on. All of this goes into the pre-training data set, and the model is trained to maximize the probability of the ground truth next word in this data set. So we do this trillions of times. And at the end, we have this model like we saw at the end of last class with the Llama 405 billion parameter base model that can generate, fluent and coherent text, but it's not really good at following our instructions just yet. So the next stage is post-training. And so here we will take this output of the pre-training stage. So note that the parameters that we start with in post-training are not randomly initialized, but they are the output of the pre-training stage, right? We don't want to repeat all of the work that we've put in training on these trillions of tokens. And now there are many different methods by which we use a smaller data set, or I could say adapt model on smaller task-specific data sets. So we could use things like supervised fine-tuning, reinforcement learning, algorithms that will basically take a much smaller data set. Usually these are of the form where the input is an instruction or a prompt, and the output is a response to the prompt. And we will optimize our pre-trained model to do better on these much smaller but more focused and aligned with human intent data sets, where really the goal in modern LLM training is to make the model follow instructions as well as it can. So we know the pre-trained model does not really follow our instruction, like it's not trained to follow our instructions. It's trained to predict the next word on this gigantic data set. The post-trained model is intended to be used as, you know, a chatbot or a coding agent or whatever. So at the end of this, we're left with our final transformer model that can be deployed to whatever application we want. So this diagram is actually quite simplified compared to what actually is happening. We might actually have like many different models that are being trained for different purposes, and you know, if you type in a particular prompt, like summarize this book, the model, this prompt might be routed to a different model than if I said translate this sentence from English to French. And especially when we get into like agents that are powered by language models, there's a lot of different sub-modules and things like that beyond just this one gigantic model. But still, like the gigantic transformer model is powering almost all of these features that we see in today's NLP or LLM landscape. And so this broad process here of pre-training and fine-tuning is an instance of transfer learning. So we're basically transferring all of the knowledge about language and the world that our model has picked up during pre-training into a model that can actually solve tasks that people care about, and that ability is unlocked during post-training. And then we will talk a lot more about what are the theories behind what kind of capabilities does a model learn in pre-training versus post-training? What is the purpose of post-training? Is it just to kind of, you know, fine-tune these capabilities that the model already had, or is it imbuing the model with more capabilities? There's, you know, a lot of these things are not solved yet, and so there's just hypotheses behind them. But what I wanted to just write down here to make it clear is that the model, the language model, is the same architecture throughout all of these processes, right? The only thing that's changing is the assignment of values to the parameters in that model, right? They start out random, then they get trained, and now they're a new you know, set of parameters for next word prediction. Then they get further fine-tuned, and then they're better at following instructions. So does this whole pipeline make sense at a very high level? Yes. Yeah, so all of these models are generally like decoder-only architectures. With a decoder-only model, you can adapt it into being like a prefix LM just by changing the mask. So yeah. Other questions? All right, let me just make sure things are working on here. Okay, assume they do. Okay, so now I wanted to just show an example of this pre-train and post-train process with a model that we're you know, not going to see for the rest of the semester, but is good to understand because you know, it was historically a very important model. And so we're going to be talking about BERT for the next few minutes. This is an example of an encoder transformer. And it also introduces a new training objective that we haven't talked about. So the pre-training objective is called masked language modeling. And the reason that we need a new pre-training objective if we're switching to an encoder model is because in an encoder, each token can see not only the previous tokens, but also all the future tokens, right? Because there's no masking happening during the training process. And so if we did next word prediction naively, this would not result in a model that has to learn anything because it already has the answer about what the next word is. And so we'll see some, the different architecture here. So, okay, maybe I'll go down here. Let's take our running example. My favorite LLM is ChatGPT. So now in normal language model training, I would just encode all of these into embeddings and then pass them into my transformer. But remember, I can't do next word prediction in an encoder. So what the authors of the BERT paper came up with was instead, let me just randomly replace some percentage of the words in the sequence with a special mask token. So here the first thing we're going to do is actually modify our input to remove certain words. So here, maybe I decide to remove 2 words, the first word and the third word. Now, I'm going to pass all of these tokens into this unmasked multi-head self-attention block and have L different layers of this. And at the end, as we now have understood, we're left with the final layer, hidden states. So now the kind of innovation of this BERT model is that we will put a softmax layer on top of each position associated with a mask token. And so that would be the first position here and the third position. And the goal is to predict not the next token, but the missing token, the masked token. So we can train this model on trillions of tokens, just like we can do with next word prediction, because we get the labels for free, right? We start with an uncorrupted sequence, and then we randomly mask out some of the words in that sequence. We pass the sequence through this encoder, and then at the end, it's asked to predict the missing words. So at this point, this is the pre-training structure of BERT. What do you all think about the potential? How does this compare to next word prediction? Are there any ways that it is worse than next token prediction in your opinion? So this is masked token prediction. Yes.
I think here we have multi-masks.
Mm-hmm.
Which can cause the issue with the prediction of words.
Yes. So here we have to pick a masking rate, right? So given a sequence, what percentage of the words am I going to mask out? And so what you bring up is a good point. Let's say I masked out 4 of these words and I only left is unmasked. What happens then is that you have almost no information with which to predict the missing words, right? So you might think, okay, well, I should use a very low masking rate so that I have as much context as possible. However, if, let's say I have a 500 token long sequence and I only mask 1 word, that means I only get training signal through 1 prediction. So I've encoded 500 words and my loss is computed only over 1 token. So I've done a huge amount of computation, but I'm not able to compute a loss at every position like I would be at next token prediction. So this masked language modeling objective can be very inefficient if I'm using a low masking rate. But on the other hand, if I'm using a high masking rate, I have this other problem where I'm losing too much context. So compared to language modeling, it's a little tricky, right? You have this masking rate that has a lot of control over how feasible and efficient the training process can be. In practice, the masking rate is something like 15 to 30% of tokens, but there have been many papers that study this. This is a hyperparameter that you can choose before starting the training process. Okay, so that is one kind of con of the setup. What's another issue with this?
On the other hand, you end up giving it too much context, so like they're also giving it like previous and later words.
Mm-hmm.
Ideally shouldn't have access.
I mean, here, so you said there could be too much context. But here, remember that regardless of how much context the model has, the input is actually masked. So the model will never get information about exactly what word is in here. However, you are right that the more context you give it, the more likely it is that maybe this word was actually repeated somewhere else in the input, and so it becomes easy for the model to just copy that over as opposed to do some complicated reasoning. Like right now, if I have blank favorite blank as ChatGPT, the model has to know a lot about ChatGPT and like what is ChatGPT? It's a language model, so maybe LLM is something reasonable to fill into the mask, right? So it does require encoding some world knowledge into the parameters in order to do well at this task. Yes?
So talking about that, how does the mask behave? For example, here the expectation is it has to be my favorite LLM is. But adding to what you just mentioned, it can be my favorite language model is ChatGPT 2, right? So is it like mask considers just one word or
Yeah, so the mask always replaces just one token. You can have contiguous mask where you have like 4 or 5 mask tokens in a row. Again, this kind of ties into the topic for the next part of the class, which is how do you segment the sentence or the input. So, ChatGPT might be 4 tokens, or it might be 1 token, depending on how you set up your tokenizer. And in general here, it's just like 30% of any of the tokens are masked without a regard for if they're next to each other or not. Okay, so one other thing I want to point out here is that this kind of model, it's very hard to generate text from, right? Because here we assume that we have context from before and after the mask token. And so at test time, if I want to generate a new sequence, I kind of have this artificial setup where maybe I construct an input like my mask and then fill in the mask token and then do like a new input, my favorite mask, and so on. But it's not the way the model was trained, right, compared to next token prediction. Because in this pre-training setup, we are randomly masking tokens where there is context before and after. So this setup is not good for text generation. That said, there are several works that try and use or like adapt these kinds of encoder transformers to generation. And more recently, when we see works on diffusion language models, they do use very similar training setups to this BERT style training. Okay, so this was the pre-training process of BERT. I think for now we'll just skip the actual fine-tuning process, but I'll describe it at a high level. Yes?
So what is the purpose of BERT then?
Yes, so this is exactly what I was going to talk about.
Okay, sure.
So BERT can't generate text, right? It can't easily generate text. So what is it actually good for? The thing is, it's good for tasks that require, like, let's say you have some input paragraph or document or sentence and you want to perform a classification task. Like I want to know if the review is positive or negative. In this case, I'm not interested in generating the review itself, right? I'm interested in processing, doing something on top of the review. So if you have these like concrete tasks where you want to categorize some texts or you want to categorize words within those texts, BERT is a pretty good model for that, right? So how it works is I pre-train this model, and then if I want to use it for, say, classifying the sentiment of a review, I would do some fine-tuning where I take the pre-trained BERT parameters and I, instead of using the softmax that is over the whole vocabulary to predict identity of the mask token, I replace that with a new softmax that just has two possible outputs, positive or negative, right? And now I take these representations that are output at the final layer here, and I have some process for combining them into a single vector. So that could be like averaging them or passing them into another transformer, using one of them, like the first or last token, whatever. I pass that into the classifier, and then I fine-tune my model to predict the correct sentiment labels that are in my fine-tuning data set. And so this paradigm of take the pre-trained BERT and then collect a tiny data set of whatever task you're interested in, like classification task, and fine-tune it, yielded really strong results back in like 2019 and 2020, before people were using like language models to do everything. So BERT there was actually like a 2 or 3 year period where all kinds of researchers and industry scientists were focused on this paradigm and how can we use it for all of these useful classification tasks that we have. Of course, now that seems like a distant memory because we don't really even care too much about those, like sentiment analysis or whatever. Now I can just, dump a ton of reviews into ChatGPT and be like, what are the common themes in these reviews, right? And I can learn a lot more about them. But yeah, so to answer your question, this is very good for simple text classification tasks, not good for generation. Yes?
I have a question for the output on the top. Are these embedding for each token or contextual embedding? What are these?
Are you talking about these here?
Yes.
Yeah, so these are analogous to the Z vectors that we get from a decoder transformer at the very top layer. So they're fully contextualized with every single other word in the sequence. Yeah.
So if we look to like a predicted mask, we need to find exact same position and then.
Yeah. So, but this is something that you already know, right? Because you have done the masking yourself, so you know exactly which positions of the sequence involve this masking. Yeah. Good question. Yes.
So it's the same process is passed through the softmax.
Yes. Exactly the same as a decoder. You use the same softmax layer, same vocabulary. Everything is the same. Yeah. And of course, you're not predicting, you're not computing a loss at any of the unmasked positions. Yes?
What's the difference in like information between a learned embedding and your output hidden states?
You mean like down here versus up here? So the very first layer, or like these embeddings, are not contextualized, right? So here, ChatGPT does not know that the second word of the sentence was favored. Every layer after that adds more and more contextualization of the representation at a current position, what were all the other words in the sequence, and how might that impact. But there have been a lot of studies on, so like this top layer representation, how much information does it have about the original word at that position versus all of the other words? It's obviously hard to tease apart, but they do contain information about the current word as well as the context. All right, so that's all I wanted to say about BERT for now. we will get into the whole fine-tuning process in much more detail after we've covered the basic pre-training stuff. Okay, so now I wanted to switch gears and talk about tokenization. So we've been ignoring this for quite some time, and it is a critical part of any sort of language model or masked language model. Even things like BERT are dependent on the tokenization. So in the process of tokenization is basically mapping raw strings into sequences of discrete tokens. And here again, we will make the type token distinction. The tokens are drawn from a vocab of types. So the tokenization process generally has two outputs. One is a vocabulary of all the word types, and the other is some sort of way that, given any arbitrary string, you can segment it into a sequence of the tokens. So just to make this more clear, let's take our example again. So the input to all of my models is going to be just the raw string that is observed in the training data set, right? So before I do any sort of neural network processing, I first need to apply this tokenization process. So here, when we put this through a tokenizer, the result is a sequence of indexes into the vocabulary. So the real kind of sequence that the model is operating over looks something like, I don't know, or something like this. So if I had, some huge vocabulary, each of the tokens in the sequence is going to be represented with an index, or this number that corresponds to that entry in the vocabulary. And now I'm going to look up for like the 71st word type in the vocabulary, what is my associated embedding with that word type. And I'm going to similarly do that for every one of these indexes. And that's how I actually obtain the sequence of embeddings that is then fed into the, my giant transformer LM. Does that make sense? So we are focusing on this process for the rest of the class. How do you get from the raw string to this sequence of indexes? So in your homework 0, we had a very easy case, right? So, well, at least easy for English. It's not even feasible or viable in other languages. Split on white space, and you can make this better if you want by also splitting on punctuation. And so this yields something that's close to a word level tokenizer. So with some exceptions, I want to split my sequence into the component words in English or other languages that are white space punctuation tokenized. However, you'll note that even in homework 0, we had a sequence where just normal white space tokenization resulted in all these weird issues, right? And it's not really the case that this is scalable or makes sense. There's a lot of weird edge cases associated with this kind of tokenization. So if we think about the sentence, Mr. O'Neill thinks LLMs aren't useful. So here, if I use my simple whitespace and punctuation tokenizer, we would split O'Neill, this last name, into two different tokens, and we might not want that to happen, right? That's a single person's name, so we might get like O plus Neil. But here we may actually want to do this kind of split, right? So something like this, or you might want some more intelligent splitting. So this one isn't particularly good. You might want something more like this. But you can see that these decisions are a little unclear, right? I might want to tokenize this aren't, the contraction, but I may not want to tokenize the name. And so I don't really have flexibility in doing this. So generally, when we're using these kinds of white space tokenizers, we need to write a lot of specialized rules to deal with each of these edge cases. And these kinds of tokenizers can get very, very complicated. So you might not, for some of these rules, you may need like syntactic parses of the sentences. You might need part of speech information, named entity recognition. So there are a lot of potential building blocks here. Some of these kinds of rule-based tokenizers are implemented in a library called Spacey. So if you're ever interested in using them, you can check it out. But overall, it's just not a scalable method, especially when you consider that modern language models are not just trained on one language, but trained on many different languages of the world, also trained on things like code, maybe even trained on images. And so you have like this white space tokenizer that just cannot keep up with the diversity and scale of the data that's coming in. So, right, it also, just to keep listing limitations, doesn't work when we don't have some easy way to split words. So, for example, Thai and Chinese, you can't use these rules for. Another thing it is not good at is handling unknown words. So, there's a ton of words in even just the English language, right? If you split by white space, there's like millions of unique words, and there's new words that are invented every day, right? Like slang or whatever. And so even if you have all possible words in English that exist now, in 2 months there might be like hundreds or thousands of new words that need to be added. So these kinds of word level tokenizers fail at capturing new words and rare words and things like that. So for a long time, and we'll talk more about these unknown words now, because it is one of the central problems that underlie tokenization decisions. We want to eliminate this problem of unknown words. We might want a tokenizer that, regardless of what string is passed into the model, it is able to come up with a representation for that. So let's say that I have the sequence at test time. I see a new word. So maybe I have something like my favorite LLM is GPT-6, right? So GPT-6 doesn't exist. This is not in your vocab. And so you have no way in the word level tokenization of handling this, right? So the default, what people do is when at test time you observe a word that's not in your vocabulary, you replace it with a special token. This UNC token associated with unknown words. So this is a special token. In general, when I talk about special tokens, there are things like the start of sequence, end of sequence, mask, or UNC here. We'll come across these special tokens more when you talk about things like padding as well, but or when we're talking about post-training and you might have like a user role and a model role and things like that. But in general, this unknown token is meant to signify that there is a word here, I don't know what it is, but hopefully I can get a sense of what it is through the context in which it's used. So I'm still able to represent the sequence. There are some problems with this approach, right? Replacing things that you don't know about with an unknown token. What are some issues with this? The perplexity can be more, meaning...
Like unknown words, like to search within the known words, it's easy, right? I mean, unknown words.
Well, you could argue that if I had GPT-6 in my vocabulary somehow, it would still be very high perplexity because it's just not been used at all or very rarely, right? So it might actually be lower perplexity if you replace it with a special unknown token. Yes?
Every single unknown word will have the same token associated with it, right?
Exactly. So one big problem is information loss, right? By replacing GPT-6 with this unknown token, I lose all information about it, right? I don't know that it had GPT in it. Maybe I have GPT-3 or GPT-4 in my vocab. I lose all information about this word. And so it's similar to just masking it out, right? I can only know about it from its context. What's another issue with this? Yes?
What if it's a contextually important word?
Yeah, I mean, it's related, right? You maybe in a lot of these cases, the word that is replaced with an unknown token is actually extremely important. Like it might be a rare entity or very important to the topic of the document, and so replacing it in this way loses a lot of information. Yes.
So even though the rare cases are rare, but the rare case accumulated, it will be a large probability. Probably it will be a little bit funky at the end when you do the inference.
Yeah, I mean, in general, if a document has an UNC token in it, it probably has quite a few UNC tokens in it, right? So you might lose a lot of information potentially when predicting the next word. Yes?
Is there anything wrong with taking the unknown and masking it and doing something like what BERT does? When you try to fill it in with something
Yeah,
that
so you
does
can
not?
try and replace this unknown token with like a best predicted alternative, but that can be very misleading as well, right? Like, again, especially in cases where there's a bunch of unknown words or it's extremely important to have that exact word identity preserved. So generally people don't do that. Any other ideas? Yes?
We can't just add it to the list of types, right?
Exactly. So this is the other major problem is that I can't just do this at test time, right? Add this UNC token and then assume that the model knows how to deal with it. It's not, if it's going to be part of the vocabulary, it actually has to be trained during training time. So this means that I actually need to train my model with the usage of this UNC token to get it to understand how to deal with it. Meaning that at training time, I actually, in all of these cases where you're using this UNC token, I'm going to replace some percentage of the rare words in my vocabulary. I'm just going to replace them all with unks in the training data and then do next word prediction. So this causes me to lose information about my training data as well as my test data, because the model needs to know how to react when it's confronted with one of these UNC tokens. Does that make sense? Yes.
Couldn't like a possible fix also be that you split the GPT-6, right? Split it so that
Mm-hmm.
new GPTs that in that part.
Yeah, so let's talk about some solutions to this, right? Let's see if it's a good time to do that. Yeah, so maybe it's a good time to switch. So one possible solution, as you suggest, is maybe I have some intelligent way to split GPT from 6 and have them both be in my vocabulary. If I can do that, that would be great. But in general, like there's so many possible unknown words that I can't guarantee a split like that is available at every for every unknown word. So let's take a look at some alternative tokenizers. And we can motivate it, this GPT-6 example is good, but we can kind of generalize this to arbitrary cases. So for example, let's take this like different forms of the same word. So if I had open, opens, opened, opening, openings, blah, blah, blah. These, in a word level tokenizer, are all represented, all different types in the vocab, which means that open, openings, opened, opens all have their own embeddings, and there's no sharing of information across them. And so what you suggested is similar to, well, what if we had a more intelligent way of doing something like open as the stem in the vocabulary, and then I might have some like suffixes in my vocabulary. Yeah, something like this, right? So this is keeping a stem and suffixes, and I could, generalize to prefixes or other, important subwords. In general, though, it's a little tricky to do this because if you wanted to actually be accurate and respect, like, get the correct stem and the correct suffix, you might need to use a morphological analyzer. So there are tools that do this for English and other high-resource languages, but there are not good tools for most of the languages in the world. And it also kind of breaks down when you're looking at code and things like that. So not really a scalable solution. We will get back to this, though, because there might be ways that, well, maybe we don't need this analyzer, but we can approximate this kind of intelligent splitting of words. The other alternative is to do character level splitting. And so here, it's actually much better for the unknown word problem, right? So if I do character level splitting, I have a small vocab, and it's very hard for me to very small number of unks. It's hard to have an unknown token if you're using character level splitting, because the unknown word would need to have a character that you haven't observed before. Now, if we're looking at something like Unicode, there's like 160,000 different characters. So actually your vocabulary is not small if you wanted to support like every possible character. However, in general, if you just support, like if you cared about English and you had all the letters and all the numbers and some punctuation, you're going a long way to reducing unks. However, there is a drawback of this, of course. Otherwise, everyone would use some sort of character level tokenization. What is a drawback of tokenizing with characters instead of words? So each character doesn't have much meaning on its own, which is true, right? Let's say I have just English letters, right? 26 letters. My vocabulary is really tiny, and I have a vector associated with each character, but it doesn't mean much on its own. That is a problem, but perhaps if my transformer is large enough, untrained on enough data, it's able to contextualize and understand the meanings of words and phrases and sentences even through the attention layers, right? So it's not like a, something that inherently is bad. Yes?
If you were trying to now train your transformer for like manipulation or like tokenization in this case, it becomes really, really inefficient.
Yes.
Because your context becomes like massive.
Exactly. So the biggest problem with this is very long sequences. And that leads into another issue that we have yet to talk about, which is what is the complexity of the transformer architecture? Why do we care if the sequences are longer? Like opening, did I spell that? Yeah, opening could be one word if we're using word level tokenization, meaning opening has its own embedding and that just gets fed into the transformer. In this character level tokenization, it's 7 different embeddings, right? So opening the word is itself this long sequence of embeddings that the transformer needs to process. And so why is that bad? Why might we not want this? So the thing is that so I'll write it down here. The complexity of self-attention is quadratic in the sequence length. And we can easily see this from just writing out how the attention is computed, right? So when we talked about computing this attention score, right, where we had Q1, Q2, K1, K2. So for a sequence of length 2, I need to compute 4 of these dot products, right? And we talked about how we do this in parallel and so on. However, if I double the sequence length, so let's say I have four tokens in my sequence, you can kind of see, right? Now I have 16 different dot products to compute. And if I double it again, right, now I have an 8x8 grid, so 64 different dot products. So doubling the sequence here means I have like 4 times the number of dot products to compute. So quickly, as the sequence length grows bigger and bigger and bigger, I have to compute many more dot products, and that begins to limit, first of all, it takes much longer, right? And then secondly, you run up on hardware limitations, like how many of these computations can you actually do in your GPU memory and things like that. So in general, when you're training a language model, you prefer to have shorter sequences, right? If you have the same input string, it's preferable to tokenize it into fewer tokens than more tokens for efficiency purposes. So there are some trade-offs, right? If you tokenize it in fewer tokens, you might deal with this UNC problem and you have other issues. But if you just use like character or even lower level, like byte level tokenization, you have huge sequence lengths and in general, that has been kind of a deal breaker for training, which is why none of the big models that we see today are relying purely on this like lowest level of tokenization. Okay, any questions about this? It is important that you understand the complexity of the transformer. Oh, I have a question about BERT. In the scenario of sentiment analysis by BERT, which masked bit is BERT trying to predict? That's a good question. I did not explain it intentionally because it adds another level of complexity that is kind of irrelevant. But in general, when in BERT, we pass some representation of the text into the sentiment classifier. So this could be like the average of all the final layer token embeddings. In the actual BERT model, they have a special token at the very beginning of the sequence that you're intended to put your classification head over. So that's how it works. But yeah, I'm not going to go into any detail. If you would like more explanation, you can check out the video on BERT in the previous semesters of this class. All right, so back to this. So we understand kind of the trade-offs now between efficiency and handling of out-of-vocabulary words and maybe more intelligent splitting of things into like stems and suffixes and prefixes and so on. I want to talk about the most commonly used tokenization strategy today, which is subword tokenization. And so this is similar to the case up here where we have like a word that is tokenized into different subwords, but not the constituent characters. We still have like a stem like open and then some other pieces of the word. So the goal here is kind of to balance character and word tokenization. So words have too many out-of-vocabulary issues. It's also hard to even define what a word means and what a word should be, and you have all these rules and stuff like that. Characters, you don't have those issues, but you have longer sequences. So the idea of most subword tokenization methods is that we want to find some balance where we can still encode the sequence in a reasonable number of tokens, but we have better ways to deal with all of the issues with word level tokenization. And almost all of the subword tokenization approaches are based around a simple algorithm called byte pair encoding, or BPE. In the context of language models, this method was again first introduced for the task of machine translation. So it's another instance where machine translation is kind of carried over into just like general language understanding today. So I'm going to explain this algorithm with an example, like a very small corpus where we can see what's happening. And then after that, we'll talk about like today, what are kind of the cutting edge approaches that might make their way into the next generation of language models. All right, so let's say I have a small corpus, not a realistic one at all. The first thing I'm going to do in byte pair encoding is generally some sort of pre-tokenization step where I might use something like white space tokenization to split into word type units, like smaller units. It doesn't really matter how good that is. I just need some way to segment the string into smaller pieces. And a lot of the approaches that people use today don't rely heavily on the step, or maybe even don't need it at all in the case of algorithms like sentence piece. But we're going to assume it here just for simplicity. So let's say I have a corpus that contains only 5 words in various permutations. So the word hug occurs 10 times, pug occurs 5 times, hun occurs 12 times, bun occurs 4 times, and hugs occurs 5 times. So in the first step, I'm going to initialize a vocabulary of just the characters. So I'm going to just have this like V0 here, indicating that this is our basic vocabulary. And it's going to have all the individual characters. So H, U, G, P, N, B, S. So I have a vocabulary of 7 characters. Now I can actually use this to segment my text. So step 2, tokenize with current vocab. So now my data set becomes something like this. H plus U plus G, P plus U plus G, P plus U plus N, H plus U plus G plus S. So this is like the most base form of the vocabulary, and we have our counts over here. All right. So now what I'm going to do in the next step is take this tokenized version of the data set and count up the frequency of all pairs of characters that occur in this data set. So let me write that over here. Step 3, count each character pair. I should say token pair in data set. And so note that here we're interested in pairs of tokens. So what does that mean? Well, I can see that if I make a new list, maybe I'll use green, pairs. The first pair I see is H plus U, and this occurs 10 times in hug and 5 times in hugs. So it occurs a total of 15 times. Then I have U plus G. So U plus G occurs 10 times in hug, 5 times in pug, and 5 times in hug. So it occurs 20 times. I have P plus U. That occurs in pug and pun. So that's 17 times. And so on. So I'll count up all of the, like how many times each pair of characters in this data set occurs. So it turns out that UG, U plus G, is the most frequently occurring character pair. So now I'm going to, in step 4, choose the most common pair and add it to my vocab, and then I'm going to re-tokenize. So my next iteration of my vocabulary contains 8 word types, not 7. It contains H, U, G, P, N, B, S, and now this pair of characters, UG. So if I re-tokenize my data set now, it's going to look a little different. So I have H plus UG. And note now, when I'm doing the tokenization, I always am going to prefer sequences that are the shortest, right? So now I actually have 2 different ways to tokenize the word hugs, or hug. I could do H plus U plus G. Those are all in my vocabulary. Or I could do H plus this new vocabulary type UG, right? So that latter one is only 2 tokens, whereas H plus U plus G is 3 tokens. So I'm going to prefer the usage of my combined merged vocabulary items. Any questions about that? Yes.
So what if next step we will put the hug into the vocabulary? Will the UG be overridden or no?
So UG will remain in our vocabulary, but hug will be a new type. So if we add hug to our vocabulary next, then this first word will just be 1 token, hug. It could be split into H plus U plus G or H plus UG or the single token hug. But since the single token is the shortest, we're going to prefer that.
So when we use the tokenizer, it have a mechanism to figure out
Yes.
if there's a whole word, we use the whole
Yeah,
word.
so it's part of that algorithm. Like based on the number of merges that have been made, you will prefer. So each of this, like UG creation is one merge, and H plus U plus HUG, if that's a single token, is going to be two merges. So we're going to prefer to use things that have been merged multiple times if possible. Okay, so now we have H plus UG, we have P plus UG, and then we still have the character level ones down here. And then we have H plus UG plus S. So now what we're going to do is just repeat this process. So I'll write that. Repeat process S times, where S is the number of steps. This today is usually something like 32K or 64K, where at each step we add one new thing into the vocabulary, where that's like the most frequently occurring thing. So like if we were to run this process on this data set, we will eventually add, maybe in the next time we add, what was it? Yeah, PU. Yeah, so maybe we'll add PU. Then we retokenize, and then next time it could be that hug is the most frequently occurring, so we'll add that and proceed. So you can see how as we iterate and do more and more steps, we'll start to form longer words, right? Like we eventually will have a lot of common words in our vocabulary just because they occur a lot in the training data set. Like here, hug is already in the vocabulary because of its frequency of occurrence. And so in general, we observe that when we run this process on real data, we get a good number of legitimate words that are showing up in our vocabulary, but we're also able to much better handle the unknown word problem. So why is that? Why is the unknown word problem not a big issue in this kind of setup?
Because it already contains all the single characters.
Exactly. We already have the base character. So in the worst case, any input string can be split into its constituent characters. Of course, on average, we hope that that's not happening, and most sequences are being split into something like words. Other questions? Yes?
So, say with GPT-5, right, where you haven't seen enough training data,
Mm-hmm.
is it still common to do 64K on average? Would be fine. Like, obviously they haven't released that information, right?
Yeah. Well, they do actually release their tokenizer.
Okay.
It is important because even the closed models, you need to be able to estimate how much will this cost if I run this amount of data through it. And the only way you will know it, because you pay by the token, is like how many exact tokens is this input going to be, and the output, like what should I set the max to be.
So then do they still find on average that 64K?
Well, again, like this S here is a hyperparameter, so we decide. I think there's, so they've released multiple tokenizers. I believe the newest one is a little more than 100K tokens. But yeah, there's always new tokenizers that are being released, and it's another variable when judging different models. Like, it really affects performance on lower resource languages. And so that's something that we'll get into a little bit here at the end. Oh yeah.
So how are the counts calculated for every step? Like, is it automatic or do we
Yeah, the counting is automatic, right? So here, based on my tokenization, I can just look at count of every pair of tokens that occur in the data set. Yeah. Okay, so I wanted to talk very briefly about what's happening today. So it's easy to understand and visualize byte pair encoding as operating over sequences of characters. But if we want to really extend this to many different languages and potentially code and stuff like that, we may have to use a ton of characters in our base vocab. And so at that point, it's more a question of, should we just run this algorithm over bytes, which is in the name, right? Or should we stick to characters? Actually, GPT-2 used this BPE algorithm over byte sequences instead of character sequences. So that was the first model that actually used byte pair encoding over byte level tokenization as to segment the input. So just to clarify, right, we have things like Unicode and encodings like UTF-8, which allow us to basically provide a way for computers to read in text, right? They provide a protocol. And in UTF-8, which is probably the most commonly used encoding, all of the ASCII characters can be represented with 1 byte. And then characters from non-Latin languages generally take 2 to 4 bytes. And the things that take 4 bytes are usually emojis and other things like that. And there's a lot of room to add new ones as well. But in total, there's 160K Unicode characters today. And so those are UTF-8 provides a way to represent each of these characters between 1 to 4 bytes. And what I wanted to emphasize is that this encoding does kind of disadvantage languages that are not represented using the Latin alphabet, right? So I think Chinese characters, for example, are usually 3 bytes. And so that means that if you're using this tokenization at the byte level, your sequence lengths are going to be much longer for some languages and shorter for other languages like English or German or Spanish. And that really does affect performance, and it's something to be aware of when you're considering tokenizers. So that kind of motivates, and many other reasons, motivated people more recently to think about, well, why do we need to have this kind of static segmentation into a vocab at all? Why do we need a static tokenization? Static meaning after I run these 32 or 64K merges on my byte or character sequence, I have a fixed vocabulary, and that's what I'm going to use to segment any text. More recent approaches have looked at dynamic tokenization. And so here, we receive a text that is in the raw byte level representation. So I'll just write it out in characters for now, but each of these characters is 1 byte in UTF-8. So this is the word favorite. And so in these new approaches, I embed each byte. But of course, this is a huge sequence length. And so what they do is have a tiny local model that's sole responsibility is to take subsequences of these bytes and transform them into a single representation. So there was this paper called Megabyte by Facebook, where they just decided, I'm going to take each non-overlapping segment of 4 bytes and pass it into this tiny local encoder. And that's going to produce a single vector that I can then feed to my transformer. So in this way, like, I'm operating over the raw byte level representation, but I'm not going to run the vast majority of my computations over like this extremely long sequence. I'm going to create a shorter sequence of these like latent tokens that are produced by the local encoder. And then I'm not going to draw this out, but once you get to the top of the network, you have to project the sequence back into the byte level sequence and then predict the next byte. And so just as a visualization, I'm going to switch over to my screen here and show you. So this figure is from a paper called, I can just scroll up here, the byte latent transformer, which is an improvement over the megabyte thing that I just talked about. So here you can see that they have a sequence better than BPE, and they have an embedding for each of the bytes in this sequence. They pass this into a local encoder, and unlike just every 4 tokens gets encoded into a vector, they actually have a more clever method that uses the entropy to determine where to split this byte stream. So here, like, this single byte is assigned its own embedding, but then this sequence of 7 bytes is all embedded into one. Now this giant latent transformer here could have your, billions of parameters that it's operating over. The local encoder is intended to be very small because, again, like, it's operating at the byte level. It doesn't have that much context. All it's doing is encoding some variable length short sequence of bytes into a single vector. So most of the parameters are in this latent transformer. These are the masked multi-head self-attention for L different blocks. Then at the end, we get these 4 final layer hidden states. So the thing you have to do now is project this back into the byte level sequence. So I get back these, 12 vectors. And then I'm predicting at the byte level as well. So you can see here, given the start of sequence token, I'm predicting the character B, right? The byte associated with this character, capital B. So they claim that this kind of approach reduces the sequence size for the vast majority of the computations here. But you can imagine that the masking in this setup is really difficult as well, especially when you have variable length segmentation. So this is what people have been exploring today. It hasn't yet made its way into any of the state-of-the-art language models, but it does have some nice advantages, so we might see it crop up in the years to come. All right, great. So see you next Monday.